be with you here in the 6th International Conference on Machine Learning. So our paper title is Hyperparameter Sensitivity Analysis of Reinforcement Learning in Autonomous Driving Environments. We start by an introduction. Why hyperparameter sensitivity matters for reinforcement learning on autonomous driving? This is the question we ask. So autonomous driving requires reinforcement learning systems to be consistent and reliable. And the performance of reinforcement learning algorithms often shows significant sensitivity to hyperparameter choices. And any small adjustments can affect the learning stability and the convergence speed and the final performance, which can lead to unreliable or inconsistent learning outcomes in safety-critical settings. So we need a clearer understanding of hyperparameters' effect to ensure robust policy development in driving tasks. Unfortunately, our current understanding is quite limited because most prior sensitivity studies focus on simple reinforcement learning benchmarks, and reinforcement and real-world driving environments are far more complex and has more variables and interactions, and the reward design itself and the complex sensory inputs can amplify sensitivity. So also, existing work typically examines single hyperparameters in isolation and overlooks interaction effects. And as a result, the tuning strategies we have now are not generalizable to complex driving scenarios. So this leads us to our objective and methodology. And our research question is, how sensitive are state-of-the-art reinforcement learning algorithms, specifically Proximal Policy Optimization and Soft Actor-Critic, to their hyperparameters in realistic autonomous driving scenarios? And our approach is to first conduct a large-scale empirical study using the high-D driving dataset, which is a naturalistic dataset from real-world data, and we use CommonRoad-RL benchmarks. Then we evaluate two major widely used continuous control algorithms, PPO and SAC. We employ Optuna to explore the hyperparameter search space with multiple seeds. And then we use functional ANOVA to quantify both main effects and also interaction effects, and identify the most influential hyperparameters for each algorithm. And we also analyze how random seed affects the performance. So now we dive deep into our experimental setup. For the environment, we use CommonRoad-RL, which is a benchmark for autonomous driving, as we said. And we use a high-D dataset, which is naturalistic highway dataset collected from real-world data. And each trajectory is converted to 40-second scenarios. The algorithms, as we mentioned, we use two widely used continuous action control algorithms, which are Proximal Policy Optimization and Soft Actor-Critic. Proximal Policy Optimization is an on-policy, stable actor-critic, which uses clipped surrogate objective. And Soft Actor-Critic is off-policy, entropy regularized actor-critic, which uses robust exploration and sample efficiency. And we implement both in stable baselines because it's integrated with CommonRoad-RL benchmark. So our reward design is implemented from CommonRoad-RL. We use sparse reward function, and it's a simple function that emphasizes termination events. So the reward step can be either goal reached or collision or off-road or timeout. Otherwise, it can be 0. These are the termination events. And this equation represents the sparse reward for each step. And as we see, it's a summation of determination events weighted by their coefficients. And the coefficients are detailed in the paper. So we use, for hyperparameter optimization and evaluation, we use Optunum with random search, and we disable pruning to obtain complete trials. We run 500 complete trials per algorithm over 5 seeds. So each seed has 100 trial, and each trial runs for 100,000 time steps, evaluated every 10,000 time steps across 5 episodes of evaluation on a separate evaluation environment. And our objective is to maximize the mean evaluation return. So for results and analysis, first of all, we explore the hypersensitivity across seeds for each algorithm. So here we see in this plot, we see a box plot for the best mean evaluation reward for proximal policy optimization. And in the paper, it's very detailed how we obtain this best mean evaluation reward. So basically, we can see here that the median reward is tightly clustered around 0. And the upper quartiles are between 4.5 and 7.2. And although some configurations perform below 0, but the overall spread is limited, and the interquartile ranges are compact, between 6.2 to 9.6 points. We also see overlap between seeds. So we see that performance variability is dominated by within seed spread, not between seeds shift, which suggests robust performance to different seeds. And also this compact interquartile ranges suggest robustness to hyperparameter choices. Now, in contrast here, we see the best mean evaluation reward for Soft Actor-Critic. And we here see much wider reward range. And the median reward spans from -20 to -9. The lower quartiles consistently near -26, and the upper quartiles range from -6 to +12. So we can see here that Soft Actor-Critic, even though it can achieve very high performance with a maximum of +50, which is the maximum reward the algorithm can get under the sparse reward coefficients we set earlier. But also it frequently produces failures with -50 rewards or less than this. So this is also the least possible performance it can achieve. So this wide interquartile range, around 20.5 to 38 points, indicates strong dependence on hyperparameter choices. Although again, the performance variability is dominated by within seed, not between seeds. So now we investigate the functional ANOVA analysis for hyperparameter importances. Functional ANOVA maps hyperparameter configurations to performance using a random forest and decomposes the variance into main effects and higher order interactions. So we mitigate the randomness in the surrogate model, which is the random forest, by repeating the functional ANOVA analysis over multiple random seeds. And here we see the main effects for proximal policy optimization. So on the x-axis, we see the hyperparameters tested, and the search space and the ranges of each hyperparameter is detailed in the paper. And on the y-axis, we see the importance. And these box plots also show the mean and the standard deviation across seeds. So we see the most important hyperparameters are the clip range value function, the value function coefficient, the max grad norm. And then we see for soft actor-critic, the main effects, again, on the x-axis, the hyperparameters, and on the y-axis, the importances. So we see the most important hyperparameters are learning starts and train frequency. Then we investigate the interaction effects, and this is the interesting part. And we see that interaction effects are significantly more important, so it has higher importance than main effects. And also, we are only showing the top 20 interaction effects because the full interaction effects for all hyperparameter pairs will take so wide picture. So this is also consistent and present in soft actor-critic as well. The interaction effects have higher importance and also, although less spread over the pairs, but it all has higher importance than main effects. And again, we also see that the most important pairs are the hyperparameters which had the higher main effects. So they dominate the main effects and the interaction effects. To quantify this, to quantify the importance of main effects and interaction effects, we calculate the main share and the interaction share. And as we see for proximal policy optimization, main effects explain around 9% of performance variance, while interaction effects account for around 91% of performance variance. Although it's less for soft actor-critic, so the main effects explain around 12%, and the interaction effects explain around 88% of performance variance, but still we have interaction effects overwhelmingly dominate the explained variance. And this means that the performance variability is largely driven by complex interdependencies between hyperparameters. So we dive deeper into these interaction effects with pairwise marginal plots generated by functional ANOVA analysis. We pick the top 4 hyperparameter from main effects and interaction effects for each algorithm, and when we plot the pairwise marginal plots. So functional ANOVA generates these plots by fixating all the other hyperparameters and only varying these each pair of these hyperparameters. And as we see, there is huge complex nonlinear interactions between the hyperparameters. So on the left, we have the interaction between clip range value function and max grad norm. And on the right, we have the interaction between max grad norm and value function coefficient. Here we see the interaction between clip range value function and value function coefficient. We also see the interaction between clip range value function and number of optimization approaches. This gets even more interesting for soft actor-critic. The complex nonlinear patterns are even more obvious here. So we have interaction effects between learning starts and gamma on the left, and on the right we have interaction effects between learning starts and tau. Then we have interaction effects between learning starts and train frequency on the left, and interaction effects between tau and train frequency on the right. So how does this add to our knowledge about hyperparameter sensitivity? First of all, we compare this to prior work. Prior studies, which investigated simpler reinforcement learning benchmarks, showed that main effects often dominate, accounting for 20 to 88% of interactions, of importance or effects, while interaction effects only account for less than 45%. Of course, this is contrasting our findings in autonomous driving settings. Also, in simpler environments, in prior work, usually one or two hyperparameters dominate the variance. This is also contrasting our studies, which finds that the variance is spread over multiple hyperparameters. So, our study suggests that for complex autonomous driving scenarios, there is more or stronger interactions due to high dimensional inputs and sensory data. And thus, effective tuning requires considering hyperparameter interdependencies, not only individual parameters. And the practical implementations of our study for the auto reinforcement learning field is to focus on joint tuning. Interaction effects dominate, so we have to focus on interaction between hyperparameters and not only individual tuning. We have to use model-based hyperparameters optimization methods which learn combinations of hyperparameters, such as TPE or random forest or Bayesian optimizers. And we have to optimize for robustness and not only rely on the best run. So we have to use median performance across seeds and report spread like we did in our study. And we have to turn functional ANOVA insights into guidelines. So now we have our 2D interaction maps. We can use these to define simple, safe ranges or dangerous ranges of hyperparameters regions. We also have to be cautious with pruning. Pruning can only, early pruning can stop trials very early and thus affect our judgment on the trials. We also have some limitations in our study, and we should keep this in mind that we only used CommonRoad-RL, which is a realistic benchmark, but it's not a real world driving setting. It's a simulation. We also used simplified point mass model. Although we used the HIDE dataset, which is naturalistic and collected from real world data. We also used a subset of the most effective or the commonly studied hyperparameters for both proximal policy optimization and soft actor-critic, but we didn't use the full hyperparameters, especially for soft actor-critic due to mixed variable types, which would make functional ANOVA very difficult. And we also used 100,000 time steps, and this is considered lower conversions. And we also reported the mean and the pairwise interaction effects only due to functional ANOVA, but there can be higher order interactions between the hyperparameters, and this can be investigated in the future. So to conclude our paper, we find distinct sensitivity profiles for each algorithm. So proximal policy optimization is driven by critic stability and value learning parameters, while soft actor-critic is driven by experience usage and training schedule. And the key finding is that hyperparameter interactions dominate performance for both algorithms. We have over 91% of variance explained by interaction effects for proximal policy optimization and 88% of variance explained by interaction effects in Soft Actor-Critic. So hyperparameters cannot be assessed in isolation in autonomous driving settings. The future directions can be to extend our analysis to other datasets beyond highways, because the HIDE datasets only explores highway driving scenarios, and also to compare more reinforcement learning algorithms such as TRPO or DQN, and move toward real-world evaluations, and also integrate safety-aware and interaction-aware tuning. Thank you so much. Waiting for your questions.